The next method we are going to discuss, it's called ANOVA, analysis of variance, and it's particularly useful when you compare means of several groups, and for example, if you have several grouping factors. Okay, so let's start with some theory. So ANOVA is analysis of variance. So it means that we are going to use variation or variance of the samples in order to see or not to see the difference. Okay, and in fact, ANOVA can be used for any cases where you have two or more groups. If you have only two groups, the result of ANOVA will be absolutely the same as the result of t-test. So you can think about ANOVA as a generalization of t-test for the number of groups more than two. Okay, and the idea is as following. First of all, we have this total variation of our values, right? And we think that this variation has two terms. The first is the variation because you have the groups, and the second is just random variation. Okay, so you can think that you have systematic variation source and random variation source. And then both sources summing up to the total variation. Okay? And then the idea is that to split the total variation to error and systematic somehow. And of course, we know one particular statistics that you can use to describe the variation, it's variance. So we are going to use variance. So we'll calculate variance for systematic part. We calculate variance for the random part, and then take a ratio. This ratio of the variances is called F ratio, and actually it's a statistic. And we know that statistics follow certain distribution, and we can use this distribution in order to see how extreme our statistics is. Okay, so that's the basic ideas. Now let's take some examples. First of all, there are two types of ANOVA. Actually, the algorithm is the same, but it's easier to explain how ANOVA works using these two types. The simplest type is one-way ANOVA, where you work only with one factor. Okay, for example, if you have diet and three different diets, it's one-way ANOVA because you have only one factor, it's diet, regardless how many levels you have. If you have more than one factor, it's n-way ANOVA. So it means that you can use ANOVA for many factors. For example, you have diet and gender. So you want to see if influence of diet depends on the gender. Okay, in this case, you will have two factors and many groups, and n-way ANOVA will work perfectly. Okay, and we are going to use the other example with this coagulation of blood for explaining the ANOVA. You remember that we have 4 diets and we have 24 animals, split it randomly into the 4 groups. And then after a while, we took a blood test and measured we made a coagulation test and got 24 values, 6 values for each. Okay, so let's see how ANOVA will find if there is any difference between the diets. So first of all, the first thing you need to do is to calculate the average values. So these are the average values, right? So you can see if you compare the average values, you can see, for example, the diet A and diet B have the same average coagulation time. It's 61 seconds, right? Diet B and diet C, they have a little bit higher time. And they also different, right? You have 66 and 68. But the question is this difference by chance? Or it's indeed systematic difference? Okay. Well, let's do that. First of all, we need to calculate variance. You remember, variance is a sum of squared distances between the values and mean divided 2 degrees of, right? So what we're going to do is, first of all, we just get rid of mean. So we just calculate the grand average here for all of these values, Okay. And then the grand average is 64. And then we subtract grand average from every value. Why? Because we are interested only in variation, in variance. So we don't need mean. And then it will be easy to calculate the sum of squared values because we already have subtracted mean, right? So if you look at this, for example, minus 2, it's just 62 minus 64. Minus 4, it's because 60 minus 64. Okay. And these are the new average values. And the meaning of the average values is following. For example, if we take minus 3, it means that this particular group, diet A, in average gave coagulation time by 3 seconds smaller than the total average. Okay. In the group B, it's by 2 seconds larger than the total average. In the group C, it's by 4 seconds larger than the total average. And finally, in group D, it's by 3 seconds smaller than the total. Now, let's think. What is the systematic and random variance? If we live in an ideal world where there is no sources of random variance, all animals from each group should have the same coagulation time. So if they take diet A, all animals should have the same coagulation time. Those animals who take diet B should have the same coagulation, right? What this time will be? Well, I think it's quite natural to take this average, right? So in average, because if the random effect varies up and down, it goes up and down, it varies randomly around zero, then the average can be a good estimate of this systematic effect, right? So that's our systematic variation. So if we don't have any sources of random variation, all animals in group A, those who used diet A, should have the coagulation time by 3 seconds small. All animals in the second diet with the second diet should have coagulation time by 2 larger, and then so on. We just continue. But unfortunately, we live in a random world, so we still have these random effects. How to calculate them? Well, if this is the influence of this is the systematic variation and this is the total variation, the random effect is just the difference of these two, right? So look, these are random effects. For example, why we have 2 here? Because if we live in an ideal world without any random effects, we should have -3. But we have this influence, random influence, and that's a 2, because 2 plus -3 will give us -1. Okay? So we got -1 instead of -3 because we have some random effect, we have some random variation. Okay? And the same here. Let's take this -1, right? Why we have -1? We have -3, its effect from the diet, and then we have 2 as a random effect. Okay. Or for example, we have 7 here. Why it's 7? Because we have this is effect from the diet, it's 4, and then this is effect, the random effect is 3. Okay. So now we know that we have the full variance. This is full variation. Not variance yet because we haven't calculated the variance. This is full variation. This is the systematic part. And this is the random part. Random. Okay. Sometimes it's called residuals because actually you take the full, subtract the systematic, and this is what is rest. Now look, now we can calculate the sum of squared values for the variance, right? Because we already subtracted mean, we just take all these values, and square them and take a sum. So this is a sum of squared values for the total variance. This is a sum of squared values for the systematic part, and this is a sum of squared values for the random part. And then you can see that actually, if you take 2.28 and plus 112, you will get exactly 340. Now let's think about degrees of freedom. In total, we have, in the beginning, we have 24 degrees of freedom, right? But then we calculated average and subtracted. And therefore, we lose 1 degree of freedom. It's 23 here. How many degrees of freedom we lose here when we compare the groups? Think, we have 4 groups. How many independent comparisons we can do if we have 4 groups? It's 3 comparisons, right? So, for example, if you are 2 persons and you would like to know who is taller, you need only 1 comparison. If you are 3 persons, you need 2 comparisons. If you are 4 persons, you need 3 comparisons, right? You can do more, but you don't need them to find out who is the tallest. So we'll use 3 degrees of freedom, 3 degrees of freedom here, and therefore this is the rest. This is how much is the rest. It's 20 degrees of freedom. Okay. So it's sum of squared values, degrees of freedom. Sum of squared values, degrees of freedom. Sum of squared values, degrees of freedom. Now if we want to calculate variance, we just take a ratio. Okay. So this is how we calculate variance. We take sum of squared values and divide the degrees of freedom. And then this is the systematic variance. It's 76 seconds. And this is the error variance. It's 5.6 seconds. The ratio between systematic and error variance is F value. And that's our F value, 13.57. Is it a big F value or not? Well, first of all, let's talk about null hypothesis here. Because usually null hypothesis means no effect. In this case, null hypothesis means that average of all 4 groups are the same. We don't see any difference. There is no difference between the average of. Now, our idea is to see how extreme this F value is relative to our null hypothesis. Can we get these samples with F value 13.57 if these samples came from population where there is no difference between average or among average? Well, we need a distribution. We need to know a distribution. Like average values of samples or variance of samples, they all have their own distribution, sampling distribution of this statistic. We have a distribution for the F value. Okay. The distribution sometimes is called also a Fisher distribution. It depends on degrees of freedom for systematic and error variance. You remember we have 3 degrees of freedom for systematic, and then we have 20 degrees of freedom for the error variance. So these are degrees of freedom. And then it shows the chance to get F value like we have, or even more extreme, if in fact the samples came from population without any difference. Let's see. So this is exactly the F value for these degrees of freedom. This is F distribution. Now let's think. If we live in an ideal world and there is no effect, the systematic variance should be 0, right? But because we don't live in an ideal world, it can be a little bit above 0. How much? Well, you can see that the biggest density is here. So this is the most common values. So it means that if we have these 4 groups, it means 3 degrees of freedom and 24 values in total, then the F value, if samples taken from populations without any difference, should be between 0 and 2. It can be 3, it can be 4, very unlikely, but it can be 4. Can it be 13.57? No way. Okay, of course the p-value will be not exactly 0, it will be something 0, 0, 0, 0. So our sample is too extreme from being taken from population where there is no difference between mean. Okay, so it means that ANOVA tells us there is a difference. So that's how it works. There are some certain requirements when you can use ANOVA. You can use ANOVA if all sample populations are normally distributed. It means that you have to make a test for every group, the normality test. Then we assume that the variance is the same for the populations. Okay. Of course, the variance of the samples are not the same, but again, you can make a test. I'll show you how to do it in R later. You can make a test if our samples came from populations with equal variance. And then, of course, the observations should be independent. They should not have any influence on it. In fact, if the first 2 requirements deviates a little, then ANOVA will work. But if you have some extreme outliers, then ANOVA is not a good choice.